Uh, so in our last class, we concluded it by discussing the two types of reinforcement learning environment, or in general, reinforcement learning problem, the model-based and model-free. Markov decision process, which is the first pillar of today's discussion, is a model or a way to model the environment in reinforcement learning realm in general. So today we'll talk about Markov decision processes as a way to provide model for your reinforcement learning agent, and dynamic programming as a way to discuss about algorithms that acts upon the Markov decision process environment, MDP environment, and provides optimal solution. Okay, so we are going to talk about the two things: Markov decision process and dynamic programming. If we have time, I will cover dynamic programming, but depending on the situation, I might postpone it to the next session. But we'll dive more into Markov decision process and talk about different aspects of MDP, and also we'll see Bellman equation as a way to address problems in the MDP environment. So Bellman expectation equations, Bellman optimization equations will be discussed. Okay, we'll also see some examples how reinforcement learning agent computes for optimal solutions. So chapter 3 and 4 will be um, will be discussed in these two major sections. The first one is MDP, second one is dynamic programming. So to recap, we say reinforcement learning is a science of learning to make decisions, right? It's learning by interaction. So we do have an agent, we do have an environment. The agent acts upon the environment and observes the consequences. And this observation could be full observation of the environment or partial observation of the environment. For each action, there will be consequence. We call it reward, right? So reinforcement learning agent, the agent might learn a policy, value function, or even model could be learned. The other one is for every action there is a consequence, and this consequence is normalized or is distributed in general over time. So the consequence of an action at time t is different from, or might be different from, a consequence of the same action on different time, like t plus one. So for every action there is consequence. Every decision, every policy affects the reward. The consequence is there, and also it also affects the agent state and the environment state. Okay. So in this lecture, we are going to consider multiple actions. That's the first thing near to the real environment in reinforcement learning. We are going to consider uh, uh, multiple actions and multiple states actually. So because last time we've been considering multiple actions but in the single state. For instance, the multi-armed bandit problem, we said at some point the agent can pull one of the many arms from the multi-armed bandit environment, but the state is simply one, right? So we were not considering any model at that time. But here we are going to consider multiple actions with multiple states in general, but we will also constrain the environment a little bit for the ease of pedagogy. The first one, we formalize the problem with full sequential structure. That means in the previous classes we have been discussing about value of states, and we were only considering, single state, like what would happen if the agent takes this action. That was the case. But in this case, we truly implement the sequential structure of Bellman equation, or the sequential nature of Bellman. Okay, Zamerkun.
Sorry, just classroom record marag.
Yeah, I'm recording. I'm recording
Okay,
it.
thank you.
Yeah, okay, thank you. So in this class, we are going to formulate the problem with full sequential structure. This full sequential structure is the true structure that resembles reinforcement learning agents, okay, in general. So we are not going to say there is this action A, what would happen, we are not going to stop by saying what would happen if the reinforcement learning agent applies this action A. We are not going to say that. We are going to say we are in state S at time t, then what would happen if the agent applies action A, and then what would happen when the agent transforms itself into or transports itself into the next state, which is a consequence of the current action, what would happen, consecutively or sequentially. Such kind of sequential traversals and analysis of the expected reward will be done in this class. Okay, so we simply formalize reinforcement learning problem as a problem with full sequential structure. So we start from some state and we continue traversing until we reach the goal state or until some threshold or episode is reached. Okay, that's the first thing. We again assume true model is given. The true model will be given as an MDP problem, like as a Markov decision process problem. So the second assumption in this chapter is we assume there is a true model of the environment. So the true model helps us to simulate rather than directly interact with the environment. Okay, so we assume there is a true model. The way to formalize that true model is called Markov decision process. I will talk about that one later. From the algorithms perspective, we consider dynamic programming because dynamic programming is a set of algorithms in general. It's a discipline or a sub-discipline, I would say, that lets you solve or that lets you come up with optimal value of states or action values in reinforcement learning environment, given the true model. Okay, if there is no true model, then the reinforcement learning agent cannot use dynamic programming as is. Okay, so for that purpose, we consider like dynamic programming given the true model of the environment, and we also consider the sequential structure or the time-wise dynamicity of the agent and its corresponding state and rewards. So we can simply say this is near to realistic form of reinforcement learning problem. So we started with the basic one. Now we are in model-based reinforcement learning. Next, we'll talk about a reinforcement learning where there is no true model of the environment, but some samples of the environment rather than the true model. Okay. So let's start by formalizing the reinforcement learning interaction. So we already discussed about this one in various sessions, but let's see how we can mathematically formalize the agent environment interaction, how we can mathematically formalize this interaction. Okay, in the previous class we said Markov decision process is there. Okay, the Markov decision process is a mechanism, a method to formalize or to model the environment, and the environment in general is characterized by the interaction between the agent and the environment itself. So the dynamicity of a given reinforcement learning environment can be modeled by using Markov decision processes. Okay. So this formalization using Markov decision process enables us to talk clearly about the objectives and how to achieve our goals in this environment. So let's consider the simplified assumption pertinent to Markov decision process. Let's assume the environment is fully observable. When we say the environment is fully observable, it means from our previous class, ST, S at time t, agent state at time t is what he observes at that same moment. Okay, this is not true usually. That means the environment is fully observable in general. At every time t, the agent is able to have the full view of the environment. This is a simplification factor. Okay, we are doing this just to simplify the reinforcement learning environment. So we assume we are going to solve a reinforcement learning problem, but for the agent, the environment is fully observable at every time span. So when we say ST is equal to OT, ST, usually we define ST as the relevant portion of the environment. So if OT is equal to ST, this means the current observation is a very relevant information for the agent. Okay. So given this, almost all reinforcement learning problems can be formalized as MDPs, given fully observable environment. So we call this one fully observable Markov decision process from our previous class. So, for instance, let's consider optimal control. We said almost all reinforcement learning problems can be formalized as MDPs. We can formalize optimal control with continuous MDP. Partially observable problems can also be converted into MDP, because we saw last time how we can, we discussed about partially observable Markov decision process. So partially observable problems can also be converted to Markov decision process. The bandits, the multi-armed bandit problem we saw last time are simply Markov decision process or MDPs or models with one state. Okay. So that being said, the simplification is already given. We consider OT is equal to ST, and ST is the relevant form of the environment. Now let's define Markov decision process mathematically. Like, MDP by itself is a mathematical representation of some decision process, right? So a Markov decision process is a tuple. Simply, we can define Markov decision process as a tuple of all possible states, all possible actions. Okay, a prediction function, a transition function, you can say. It could be stochastic or deterministic, and this discount factor. So a Markov decision process simply is represented as a set of possible states, all possible states, a set of all possible actions given some environment. Okay, so we are trying to model the environment with all possible states, all possible actions, a dynamic function called prediction P that lets you know what would happen if you apply some action given some state. Okay, so for instance, the happenings are formalized in terms of reward and the next state. So this we call it simply a transition model. Here we have another one called discount factor. We'll talk about this one. We have already discussed about this one from the Bellman equations perspective. The same thing is true here. So we see the importance of immediate rewards compared to long-term rewards. So basically, MDP is a model uh, which is an abstraction of the environment, and the environment is supposed to be addressed or accessed by the reinforcement learning agent. So here we are trying to formalize, or we are trying to model the environment in terms of all possible states, all possible actions, the prediction or transition function, and discount factor. The discount factor could be a single constant, real number, or it could be decaying real number, a number that decays its value or discounts its value over time. So as I've already said, P simply defines the dynamics of the problem, because it's there to predict the rewards in the consecutive state given the current state and the current action. Okay. So when you marginalize out the state transitions or expected rewards, you can come up with such kind of equations. The dynamics, like the prediction S prime given S and A, is equal to the sum of the probability, the joint distribution of the next state and reward given the current state and action for all available rewards. The reason we are saying for all rewards, the summation is done for all rewards, is that since we have, the full observation of the environment, we know what would happen when we apply some kind of action. So we can iterate over all those rewards and then the probability of some reward and corresponding next action given the current action, and know the probability of the next action given the current state and action. Okay, this can be marginalized into the expected reward equation, the expected reward given the current state and action. This can also be marginalized out in terms of reward and next action. For all rewards and next actions, we can compute the cumulative joint distribution of rewards and next actions given the current state and action ማለት ነው። So basically እዚህ ጋር ምን እያልን ያለ ነው? Markov decision process for ለምሳሌ for every expected reward given some action and state can be computed stochastically. So if you convert this one into some kind of algorithm, you may get some kind of outer loop which iterates over all possible rewards, and inner loop which iterates over all possible next states. Okay, and inside that inner loop you will have a function that computes the probability of reward you are considering here, and some next state given the current state and action. So this is kind of iterative process. This is evaluation kind of process. We'll talk about that one later, but we simply represent this prediction function or dynamic function as this one. And I think you are aware of such kind of equation. The expected reward given S and A is known from our previous class. But here we are trying to come up with rewards or the probability of some next state given the current state and action from the perspective of rewards and next states. We'll elaborate more this one in the next consecutive slides. So the alternative definition for Markov decision process is again a tuple. We can consider Markov decision process or the model of reinforcement learning as a tuple of all possible states, all possible actions, the probability function or the prediction function, I would say, the reward. Okay, here we have a little bit different definition given this marginalization. We considered reward here and discount factor. So read as the probability of transitioning to the next state given a state S and action A. So basically, reward is a function of state and action. That means the function of, or its output of applying action A on state S. This is what we discussed last time, right? So there is no new concept we are conveying here. So reward can also be rephrased as the expected return. So reward can be expressed as return or cumulative reward given state and action. And we know about the gamma or the discount factor from the Bellman equation we have discussed last time. So this ranges from 0 to 1. It's kind of real number. It helps you to discount the value, the current value of future rewards. That's the purpose of this discount factor. The discount factor helps you to compute the current value of future rewards. So that's it. We'll discuss about why we need this, how we could use it. We'll discuss that. So one of the properties, when we say Markov property, we are referring to the situation where the future is independent of the past given the present. So we discussed this one in different mathematical formalizations. We said an MDP is all about being able to come up with S at T, which is agent state, which is a relevant representation of history, and that history should be a compressed form of the whole environment, like the compressed form of the environment, which is relevant to the agent. So given that, we can define Markov property in the following manner. Okay, but the concept is this one. When we say Markov property, we are referring to the property where the feature is independent of the past given the present. So the feature is usually dependent on the present. So let's define that one, or let's formulate that one. So consider a sequence of random variables, S at T. For instance, this simply is to represent the agent state. So it's indexed by time. So a state S has the Markov set of states, S capital. The probability of the next state given the current state is equal to the probability of the next state given history and the current state of the agent. This is what we defined last time when we talk about Markov decision process, right? So this is, again, for all possible histories, H at T minus 1, H at T minus 1 is S1, S at T minus 1, A1, H at T minus 1, like this. So it's we discussed about this SARSA type of thing, like SARSA type of thing when we discussed about history last time. So basically, Markov property is the property that defines or that ensures the future is independent of the past, but the given state or the current state. And so some transition function or some prediction function P provides us with a probability of transitioning to the next state S prime given the current state, and the result of this probability or the degree of this probability should be the same as the probability of getting the same next state given the total history or view of the environment. So this is what we call Markov decision process. Markov decision process or Markov property in general. Okay. So from the ST perspective, once you know the state, you may throw the history away. This is one of the things we have been discussing last time. For instance, we discussed about ST, the agent state, and the agent state is some form of abstraction of the history of that environment with respect to the agent. Once we are able to calculate ST, the current agent state, according to Markov decision process, we shouldn't be dealing with the history because the history is already compressed and abstracted and represented in the form of ST. So this is what these statements are trying to say. So let's test your understanding. I want you to be interactive enough. Which from this, assume there is this Markov decision process, and which formalization of MDP is true, or MDP property is true, for instance. Here, the first one says, probability of the next state given the current state and action is equal to the probability of the next state given some kind of history or sequence of states and actions up to the current state of the agent S at T. Yeah. Is it correct or is it not correct? I want you to interact because interaction is a good way for understanding these gibberish things. Maybe if they're appearing as gibberish thing for you, I'm not sure. What do you think? Is the first statement correct?
Yes, correct. ግን ሂስትሪውን እንትን እንላለን ብለናል፣ ያው እንተዋለን ብለናል፣ ግን ኮሬክት ነው።
Exactly. Okay, nice. The first one is correct because the reason for this one is this is the typical property of Markov, right? Markov environment. We say the probability of the current state, the next state, given the current state in action, should be tantamount to the probability of the next state given the history. So that's one. How about the second one? How is it even different from the first one? Okay, anyway, I want you to interact, okay, if possible. So the second one is also correct. In the second case, for instance, it says the probability of the next state given the current state and action is equal to the probability of the next state, okay, given the history of states, consecutive states, and the action at time t. Specifically, we are not talking about the action in the history, all possible actions that, or all actions that appeared so far, but we are talking about actions at time t, the current action. So this is also true. This is also true. The third one, the probability of the next state given the current state and action, which is the same as the previous one, is equal to the probability of the next state given the sequence of states. This, okay, is it correct? You said correct or incorrect?
Correct.
You said correct. Okay.
I said incorrect.
Oh, Zamerkun said incorrect. Okay. Who said correct? I want some clarification. Okay, Zamerkun, if you can you just say
like
why it
the
is
future
incorrect?
state will incorrect.
Okay, interesting. I think you are on the right direction, but I'm not sure. Maybe I have to give you some more time to explain. But let me give you more insight then. The probability of the next state given the current state and action. This equation considers action, right, to determine the probability of the next state. But the latter one does not consider action. Okay, it only considers the history of states. So this is not a Markov property. This is not a Markov property. Action, if we'll come to the other one here. If one transition model considers actions to predict the next state, then there should be another transition model dependent on the history and the action in order to come up with a probability for the next state, which is tantamount to the probability determined by the previous one. So we considered action. Action is another parameter for this one. So if we consider, because last time we said, an action, the action is the driving factor, even to come to transition from one state to another state. So if the first transition model is considering action, and if the second one is not considering action, so there is a huge parameter difference. So there will be a huge prediction difference. So that's why it's incorrect. So it's incorrect, and the reason is that one. So from this perspective, for instance, the latter one, the fourth one, is correct. So the probability of some reward, next reward R and next state S, given the current state, is equal to the probability of this reward, the same reward and next state, given the history of the states in general, sequence of states. So here it's considering only sequence of states. So if an agent is considering only the sequence of states and come up with S prime, then the same agent or any other agent considering sequence of states up to the current agent state should provide the same type of probability for S prime. So in that case, the first one is true. So this actually examples lets you understand what really is Markov property or Markov decision process as a model for reinforcement learning in the time. Now let's see how we can build a Markov decision process or a Markov model for your reinforcement learning problem. Let's consider a robot that cleans soda cans. So soda can clean a robot consider assume it has two states from the battery perspective, okay? The high battery charge or low battery charge state there are assume three major actions in different states. In the state of high, when the robot is at high state, then it can only have two actions. The first one is wait and the second one is search. But if it is in low state, then it should also recharge. It should be able to recharge. So we have additional one action here. So in general, we do have capital A, which is set of all possible actions: recharge, search, and wait. Okay, but in case of high, we have wait and search. In case of low, we have wait, search, and recharge. So the dynamics, the transition model, let's assume it's stochastic model, and let's say the probability of high given current state high and current action search, let's say it's alpha. Okay, then the probability of low given high state, current high state, and current action search can be considered as 1 minus alpha. Okay, so in this case, the reward could be expected number of collector cans in case of deterministic scenario, or actual number of collector cans in stochastic scenario. So let's see a table for the robot MDP. Let me start from the bottom one, for instance. Assume the current state of the robot is at low battery state, and the action is recharge. Okay, then the probability of getting the next state of the robot low is 0 because it was in low state, it's recharging, so the next state should be high. So for that purpose, the probability of getting low next state given low current state and action recharge, we are not considering the resolutions, those high level resolutions between high and low. Like you can say 50% full, 60% full, 90% full. But for the ease of pedagogy, what we are doing is that if the agent state is low and if you apply action recharge, then it should transition to high state. Okay, that's the degree of granularity we are considering. So for instance, we might say from the MDP model, we might say applying recharge on a low state has reward 0. Applying recharge on low state, whether it is to transition it to high state or low state, its corresponding reward is 0. Okay, because the purpose of the robot is what? It's to clean soda cans. So recharging is an extra thing for the robot. So the other one, applying weight, the robot has this action called weight. Applying weight on the current state low provides you low with 100%. The probability is 100%. The same is true for all others. So we can come up with this state space type of graph to represent the different states of the robot. Here we have two states of the soda cleaning robot, the corresponding action, and the corresponding reward for that action, and the probability of that next state given that action is given here. For instance, the probability of getting low given the current state low and the current action weight is what? 1, right? If the robot is waiting at a state of low, the robot, it will stay at low state of battery. So the reward, the corresponding reward is R weight, some kind of variable. Okay, you can assign some value because the entity which is responsible to provide rewards is a domain expert or the environment itself. Let's see another example, for instance. The probability of getting next state high given the current state low and the current action recharge is 1, and its corresponding reward is set to be 0. So this graph in general is an MDP graph, Markov decision process graph, that resembles how the robot acts and how it gets or how it will be affected by the consequences of its actions over time ይለውን በደንብ የሚያሳይ ይሆናል ማለት ነው። Now let's formulate the objective then. So the main objective of this reinforcement learning agents is to maximize the returns, cumulative returns or cumulative rewards, right? So let's talk about rewards or returns then. So in this MDP environment, for instance, we took some simple example of MDP, like for the can cleaning robot. Assume this is an MDP environment. So for acting in MDP, this Markov decision process environment or model results in immediate rewards. For instance, if you are in this state and if you act some kind of action, say recharge, then you will get immediate reward 0. Okay? So acting in MDP results in immediate reward RT, R at time t, which leads to returns G at time t. We know how this RT leads to GT, right? We discussed about this one in our previous class. So GT is the sum of the immediate reward and all consecutive long-term rewards. And this can be represented or marginalized in this form, okay? It's the sum of all rewards from the immediate reward to the last reward. So this T might describe the lifespan of the agent, or it might describe the end of the episode, like the number of steps the episode ends, okay? So for all those, the cumulative rewards are added here. So here, we are not discounting anything. So for that purpose, we say it's undiscounted return. So usually, undiscounted returns are used for episodic or finite horizon reinforcement learning problems, okay? That means if, for instance, you know 10 steps would be enough to calculate the return of a given state or some action, then you may not have to discount the 9 consecutive long-term rewards. You can simply consider their value as it is tantamount to the immediate reward. That's one case. But usually, even in episodic and finite horizon, you might have to discount the rewards, because always the current value of future rewards is not the same as the immediate reward. Okay, that's true. We'll also correlate it with the human characteristics. Humans usually tend to be attracted to immediate rewards rather than long-term rewards. Okay, so the value of long-term rewards is less than the value of immediate rewards usually. So we're talking about the objectives of reinforcement learning or in MDP environment, which is return. We have undiscounted return, and it's applicable in episodic or finite horizon environment usually. The second one is discounted return. Again, as I already said, we could use discounted or gamma factor for finite horizon. So here, discounted return is applicable for both finite or infinite horizon. So here brings us to the equation called Bellman equation, or discounted cumulative reward equation. So GT here is RT plus 1, which is immediate reward, plus discounted subsequent long-term rewards. So which it can also be marginalized into discount factor times the corresponding reward at time t. The subtype of return is average return. Average return could be used for continuing infinite horizon problems. So you could use, for every time t, you could use the number of steps before it, and and use it as a denominator to calculate the mean of those rewards so far. So this and discount return, average return are simply random variables that depends on MDP, the model, and the policy. So here we have two major things. The first one is the model, which is the imitation of the environment, and the policy. The policy is there to come up with or to generate suitable actions for each state or for each time ማለት እንችላለን ማለት ነው። Okay, more on discount returns. So for infinite horizon, when you say infinite horizon, then the number of steps of the agent is like infinite. It has no end. So in such kind of situations, we use, as you already said, we use discounted returns, the main objectives of the reinforcement learning agent. So here we said the cumulative reward is the sum of the current or the immediate reward and discounted long-term rewards. So here we see some kind of recursive function. We already defined this one in terms of Bellman equation last time, so we don't really have to discuss about this one. So where do you think in this kind of situation, for instance, if there is no end for your agent's search or exploration, where do you think we should stop? For instance, I want you to interact here. የቱ ጋር ማቆም? ለምሳሌ ኢንፊኒቲ እያለን ነው እና ኢንፋናይት ነው እያለን ነው እና then for instance infinite is infinite. So is the agent going to explore like for eternity, or what is the idea here? Who can give me some insight? According to this equation, and ሲደመር 0.9 times and which is 0.9 አይደለም? Again 0.9 times gamma is less than 1. So ነገር ግን gamma if it is close to 0 we call it myopic evaluation ይባላል። close to 0 ሲሆን ለምሳሌ 0 እዚህ ጋር ብታስገባ ኢሚዲየት ሪዋርዱ ብቻ ነው ገኖ የሚወጣው ማለት ነው። ስለዚህ like far sighted አይደለም like ወይም like mid sighted አይደለም like consecutive ሪዋርዶች ጥቅም የላቸውም ብሎ የሚያስብ ከሆነ አንድ ኤጀንት ምን ያደርጋል? even it doesn't have to calculate this, by the way. So 0 ሆነ ማለት it doesn't have to calculate this one. So rt plus 1 ብቻ ለእያንዳንዱ ኢንተራክሽን እየወሰደ ይሄዳል። ይሄ ማለት ማዮፒክ ኢቫሉዌሽን ያለው የትኛው መሰላችሁ? አንድ ስቴት ብቻ አለ ብለን ቻፕተር 2 ላይ ያየ ነው ኮንሰፕት ማለት ነው። if you make gamma close to 1 ወደዛ እየጨመራችሁ የምትሄዱ ከሆነ ግን ምን ይባላል? far sighted evaluation ይባላል። ይሄ ማለት ምንድነው? These subsequent rewards are really important as the immediate reward is, the same way as the immediate reward is important ማለት ይቻላል። እንደው ኩሙሌቲቭን ከዚህ መልስ ያሉትን ወደዚህ ብትሰሩትና ብትደምሩት ከዚህኛው ሪዋርድ የተሻለ ቫልዩ አንድ ለተጠጋ ዲስካውንት ከሆነ ዲስካውንት የሚደረጉት በተጠጋ ዲስካውንት ፋክተር ከሆነ ዲስካውንት የሚደረጉት then ምን ይባላል? ፋር ሳይትድ የሆነ ኢቫሉዌሽን ቴክኒክ ነው እየተጠቀም ያለ ነው፣ ፖሊሲ ኢቫሉዌሽን ቴክኒክ ነው እየተጠቀም ያለ ነው ልንል እንችላለን ማለት ነው። we discussed about the reason behind discounting. Because Markov decision process usually discounted ነው። አንደኛው ምንድነው? immediate rewards may actually be more valuable የሚለው ነው። ኦኬ ለምሳሌ earning interest ለምሳሌ immediate earning interest is more valuable። ወደ human behaviorም ስንመጣ human behavior shows preference for immediate reward። ይሄ አንዱ ነው። ከሶሉሽን ሳይድ የመጣንበት ወይ ደግሞ ምንድነው? ዲስካውንት ሪዋርዶችን ዲስካውንት በማድረግ ይሄንን ሪዘንብል ማድረግ ይሄንን ኔቸር ዲስካውንት በማድረግ ሪዋርዶችን እንትን እንላለን። ሌላኛው ኢምፖርታንት ነገር ደግሞ ቅድም ጠይቄያችሁ ያልመለሳችሁት ኢንፋናይት ሪተርኖችን አቮይድ ያደርጋል። ለምን? ለምሳሌ እነዚህ ዲስካውንት ፋክተሮች ኦቨር ታይም እዚህ ጋር እነዚህ ዲስካውንት ፋክተሮች ኦቨር ታይም የዚህን ኮንትሪቢዩሽን ወደ ዜሮ ያስጠጉታል። ስለዚህ ሰም ኮንቨርጀንስ ትሬሾልድ ዲፋይን አድርጋችሁ በኢንፋናይት ሆራይዘን ላይ ሪንፎርስመንት ለርኒንግ ኩሙሌቲቭ ሪዋርዶችን ካልኩሌት እንዲያደርግ ማድረግ ይቻላል። ኦቨር ታይም ኩሙሌቲቭ ሪዋርዱ ለዋናው አታይም ቲ ፕላስ 1 ካልኩሌት የምታደርጉት ኩሙሌቲቭ ሪዋርድ ከአታይም ቲ ከነበረው ኩሙሌቲቭ ሪዋርድ ጋር ያለው ዲፍረንስ በጣም ትንሽዬ ሲሆን ወይም ተመሳሳይ ሲሆን ኮንቨርጅ እያደረገ ነው እንላለን እናቆማለን ማለት ነው። ለዚህም ይጠቅማል ዲስካውንት ፋክተር ኢንፋናይት ሆራይዘን ላይ ሪንፎርስመንት ለርኒንግን ኢኔብል ለማድረግ ይሆናል ማለት። ስለዚህ the way to think about it is reward and discount factor together determine the goal ማለት ነው። ስለዚህ ጎልን ዲተርማይን የምናደርገው together with these two things ነው ማለት ነው። The other thing in reinforcement learning is maximizing policy ነው ወይም coming up with optimal policy ብለን ያወራነው as an objective of reinforcement learning. So basically maximizing expected return ስንል it's all about trying to come up with a policy that will let you maximize your expected return ነው basically ማለት ስለዚህ ፖሊሲ ስንል basically ምንድነው የአንድ reinforcement learning ፕሮብሌም ሞዴል ላይክ የፕሮብሌሙ የሶሉሽኑ ሞዴል ነው ማለት ነው የሪንፎርስመንት ለርኒንግ ሶሉሽን ሞዴል ነው ማለት ነው ቤዚካሊ አንድ ፖሊሲ ኦቨር ዲፍረንት ታይም ዞን ወይም ኦቨር ዲፍረንት ታይም ምንድን ነው የሚባለው ታይም ስፓን ዲፍረንት አክሽኖችን ጀነሬት የሚያደርግ ማሽን ነው ማለት ነው ቤዚካሊ ፈንክሽን ነው ሶ the goal of reinforcement learning using this policy that or finding this policy that maximizes the expected return ነው ማለት ነው so policy ላይ ትኩረት ማድረግ ከዚህ አንፃር በጣም ወሳኝ ነው ማለት ነው so we said last time policy is a mapping between a mapping from states to action ነው ብለናል with some degree of probability ማለት ነው so for every state S assigns for each action A which is an element of all possible states of action the probability of taking that action in state S can also be defined as a policy, stochastically. So, stochastic perspective, policy pi can be defined as the probability of choosing some action A given some state S እንደማለት ነው. Okay? Again, deterministic policies are also there. So, deterministic policies ስናይ ግን for sure የሆነ policy at given state S at T, agent state S at T ምን ጀነሬት ያደርጋል ወይ ምን አክሽን ይሰጠናል የሚለው ምናቅ ከሆነ ምንም አይነት ጆይንት ዲስትሪቢዩሽን አያስፈልገንም a at t is equal to pi of s at t በምን ልናስቀምጠው እንችላለን ማለት ነው this is how we define policy stochastically and deterministically that being said about policy now let's talk about value function by the way it seems we are repeating what we have already been discussing about like value functions policies agent state action value we have already discussed about that one but considering only a single state environment now we are considering multiple state environment with multiple actions so it's better to underline on this baseline okay so the value function now since we have already defined what policy is stochastically and deterministically the value function can be defined over a policy pi ማለት ነው okay and we said the reason we come up with this policy pi in between this is that we are considering subsequent states, not a single state. So for that, we are considering subsequent actions. And the source of those subsequent actions is the policy in that environment. Okay? So the value function over a policy pi, this policy pi is there to generate different sets of actions in different time and for different state of the agent. Okay? So the value of state for over a policy pi is the expected cumulative reward or return given the current state and what? Policy, mind you. In the previous class, we were saying the value of state is equal to expected cumulative reward given the current state and action number, middle column. Okay? But now we replaced action with policy. The reason? We are considering sequence of states, so that we are considering sequence of actions potentially. So the only function that generates sequence of actions in a dynamic way is policy. So that's why we're considering policy. In a full-fledged manner, this is how we define value of state. Value of state. The same is true for action value, Q function. So the action value given some state S over a policy pi is equal to the expected cumulative reward or return given the current state, the current action, and policy, and the policy. So the reason behind this, is that we choose action A, for instance, from all possible sets of actions, okay? Then, while traversing through different value of states or different states of the agent, this action might be, applied at time t, and it might not be applied at time t plus n, okay? So this is very important for us because whenever an action is applied at time t, then the result of this policy is kind of Boolean value, which will be 1. Whenever some action is not used at some state t of the agent, then this policy will generate 0 as a corresponding result of this one. So this is basically a utilization mapping between the policy, the result or return, given the current state, the current action, and pi. Whenever an action is applied at some time corresponding value that is set to neutralize the whole equation will become 1. But if some action is not used at some time t, then its corresponding value will be set to 0. So multiplying 0 with anything is 0. So for that purpose, at that point, this action will not have impact for the summation operation ማለት ነው። በዜሮ እየተደመረ ሜድ ያደርጋል ማለት ነው። ሶ አክሽን ቫልዩ ከፖሊሲ አንጻር በዚህ መልኩ ይብራራል ለማለት ነው። ሶ ቫልዩ ስቴት ኦቨር ሁለቱን ስናገናኘው አክሽን ቫልዩ እና ቫልዩ ፋንክሽንን በዚህ ኢኩዌሽን ማገናኘት እንችላለን። ቫልዩ ኦፍ ስቴት ኦቨር ፖሊሲ ፓይ ኢዝ ኢኳል ቱ for all actions the sum of the product of the action values for that specific action. ይሄ ምን ማለት ነው? Assume we do have action A, okay? So a value of state over pi calculate ማድረግ ከፈለግን for all possible actions if that action is used ለምሳሌ እዚህ ጋር ታያችኋል። ቅድም ፖሊሲ ዲፋይን ያደረኩበትን መንገድ አትርሱ። ልክ እዚህ ጋር stochastically if this action is used at this time ለምሳሌ ምን ይሆናል? this will be calculate ሲደረግ ባየነው መልኩ then this result will be updated ማለት ነው፣ ሰም ይደረጋል። ነገር ግን if this specific action okay is not used at some point time like at some time t ምን ይሆናል? probability of a this action given some s 0 ይሆናል ማለት ነው። 0 ሆነ ማለት 0 times any action value of that corresponding action at that time will be 0 ይሆናል። so effect አይኖርም። ስለዚህ አክሽኑ አፕላይ የተደረገበት ሞመንት ላይ ብቻ for all consecutive states or for all states in that MDP ወስደን የምንሰራ ከሆነ value of state over pi እንላለን ማለት ነው። okay so given this value of state over pi let's talk about the optimal value of state አሁን ደግሞ okay እዚህ ጋር ምን እያልን ነበር? for all actions ይሄን ካልኩሌት እያደረግን ነበር አክሽን ቫልዩን እና value of state አንድ ላይ አድርገን ማለት ነው። ግን let's see what it means to be an optimal state value function ወይም value of state function ምን ማለት ነው? so ባለፈው argmax ብለን value of state over pi ብለን አውርተናል። okay ስለዚህ the optimal policy ምንለው ደግሞ ምንድነው? ፎርማላይዝ ስናደርገው the optimal value of state ምንለው the optimal value of state is the maximum value of state over pi given all possible policies in that reinforcement or MDP environment ማለት ነው። so 10 ፖሊሲ ሊኖራችሁ ይችላል። so for each of this policy value of state consecutively over this policy pi calculate ይደረጋል። so 10 የተለያዩ ቫልዩዎች ይኖራቸዋል። so from those 10 የተለያዩ ቫልዩዎች the maximum one will be taken ማለት ነው። so optimal value of state ምንለው ይሄንን ነው። so we didn't say optimal value of state over pi አላለም እዚህ ጋር mind you። ለምንድን ነው over pi ያላለው? if we say over pi we are only considering one pi, right? so we cannot compare between pi's or policies. since we are looking to compute or to compare between or among different policies for a specific state S, then we say value of state over the value of state optimal value of state is equal to for like from all policies the value of state over pi with maximum value ማለት ነው እንዳል the same is true for the action value ማለት ነው። action value from all policies the policy that provides the greatest cumulative reward is taken as the optimal action value ብለን ልንሄድ እንችላለን ማለት ነው። an MDP is solved if we know or when we know the optimal value function ማለት ነው። so MDP እንግዲህ solved ነው የምንለው በቫልዩ ኢትሬሽን ሊሆን ይችላል፣ በፖሊሲ ኢትሬሽን በዚህ ኬዝ ወይም በዚህ ኬዝ መቼ ነው ኦፕቲማል ቫልዩ ኮምፒውት አድርገን ማግኘት ከቻለን ነው ማለት ነው። ስለዚህ ሁሉንም አክሽን ቫልዩዎች given the current state and action ወስደን ኮምፒውት ካደረግን በኋላ the maximum of all ወስደን የምንሰራ ከሆነ then we solve the MDP ብለን እናወራ እንችላለን። ሶልቭ እንደተደረገ ኮንሲደር እናደርጋለን ማለት ነው። so we are talking about optimality of policy. so let's address it from the partial ordering perspective over policies. ለምሳሌ partial ordering ስንል it's a mechanism to compare one entity with the other entity, right? Simply. So a given policy pi is greater than or equal to some other policy pi j, okay? If and only if for all states the value of state over policy defines ስናደርግ ምንድነው አንድ ፖሊሲ ከሌላ ፖሊሲ እኩል ነው ወይም ይበልጣል ብለን የምናወራው for all states ያ ፖሊሲ የሚያመጣው value of state over that policy ማለት ነው ከማጋ እኩል ከሆነ ያ ፖሊሲ the next policy ሌላኛው ፖሊሲ on that state consecutive state የሚያመጣው value of state ጋር እኩል ከሆነ ወይም የመጀመሪያው ከበለጠ then የመጀመሪያውን ፖሊሲ ከሁለተኛው ፖሊሲ ይበልጣል ወይም እኩል ይሆናል ብለን እናወራለን for all states ማለት ነው። ኦኬ ይሄ በጣም ኢምፖርታንት የሆነ ኮንሰፕት ስለሆነ ስለዚህ ይሄንን ዲፋይን ሲያደርግ ምንድነው basically equal to like n like pi greater than or equal to pi j አንድ ቫልዩም ሊሆን ይችላል pi አንድም ሊመጡት value of state over pi እኩል ሊሆን ይችላል for the same state ማለት ነው multiple ፖሊሲዎች ስለዚህ ይሄ partial ordering of over policies ምንድነው የሚሰጠን list of optimal policies ይሰጠናል ማለት ነው ስለዚህ ያንን ካለን let's talk about finding optimal policy we already said that but an optimal policy can be found by maximizing over the optimal action value so a given optimal policy is the one which provides the maximum action value right the maximum action value provide የሚያደርገን ነው ማለት ስለዚህ ምን እያልን ነው በፎርማላይዜሽን the maximum action value የሚያመጣን action ከሆነ ይሄ ፖሊሲ ጀነሬት የሚያደርገው then it is what it is optimal policy ነው እያልን ነው okay so now let's go back to Bellman equation እንግዲህ Bellman equationን እስካሁን በተለያየ መንገድ አድሬስ እያደረግነው ነበር ቀጥታም last week or week before በነበረን ክላስ ላይ Bellman equation ከዲስካውንት ፋክተር ፐርስፔክቲቭ ዲስከስ አድርገናል now multiple state ላይ ስንመጣ Bellman equation really makes sense because last time we said Bellman equation some kind of recursive function ነው ብለን ስናወራ we were only considering a single state እና how can we apply recursive functions on that single state የሚለው question ነበር ነገር ግን since we are considering sequential states here we can gracefully talk about Bellman equation so from value function perspective the value of state gives the long term value of state ያ ቀደም ያለው cumulative rewardን ይሰጠናል ብለን ያወራነው ነው recursively ደግሞ በምን መልኩ ይብራራል immediate reward the expected immediate reward plus discounted cumulative reward or cumulative return given the current state and policy ብለን እናወራው እንችላለን እያልን ነው then finally marginalize ስናደርገው for any action value of state ስንሰራ ማለት ነው over policy ምን እንችላለን እቺኛዋ ለምሳሌ for all actions ማለት ነው if the action is used for a given state then its corresponding value will be 1 a flag okay 0 and 1 flag ነው ማለት ነው እዚህ ጋር የምንጠቀመው አንድ variable ነው that's the first one the second one for all since we are using model we know the reward and consecutive states subsequent states እናውቃለን ስለዚህ for all rewards and consecutive states the probability of the reward the specific reward chosen okay probability እንዴት ይሰራል የሚለውን አይተናል 1 0 ምናምን እያለን 1 minus pi 1 minus alpha minus 1 እያለን so this is basically value of state over pi can be defined as for an action used for that specific state or for an action with possibility to be used for that specific state it's the sum of the product of the probability of this combination reward and the next state given the current state and action and the sum of the reward and the discounted cumulative return ማለት ነው for the next consecutive states ስለዚህ ይሄ I think this is simply ማን ነው Bellman equation ነው ማለት እንችላለን እቺን የምታገኙት እዚህ ጋር Bellman equation ነው so you can define stochastically the value of state over pi in terms of Bellman equation ማለት ነው so basically the core function is this one r is immediate reward plus discounted value of state prime over pi but this is discounted with some kind of probability because we are talking about stochastic reinforcement learning environment ስለዚህ እዚህ ጋር r እና s ይሆናሉ ብለን እያወራን አይደለም ያለነው with this degree of probability r እና s ይሆናሉ እያልን ነው okay then እዚህ ጋር ደግሞ ስንመጣ ይሄ አክሽን applicable የሆነበትን እንትን ካውንት ማድረጊያ ቴክኒክ ይሆናል ማለት ነው። so whenever this action is used for this state on this state then this will be computed. Whenever this action is not used, this will not be computed ማለት ነው። so value of state over pi በዚህ መልኩ ይሰራል። I'm not sure if I explained it well or not. If you have question you can raise please. The second one is action values. Action value ስንመጣ ተመሳሳይ ነገር ነው የምናየው። action value over pi is expected cumulative reward given the current state and the current action and policy pi. ስለዚህ እዚህ ጋር ስንመጣ expected reward recursively expected immediate reward plus discounted cumulative reward ብለን እንሰራለን given the current state and action. This is what differentiates. So we can marginalize it like this. So we compute the probability of R and S prime to sum or to apply the Bellman equation, R plus discounted cumulative reward. This discounted cumulative reward ደግሞ በምንድን ነው የተሰራው? ቅድም ሪሌት ባደረግንበት መልኩ ልክ ቫልዩ ኦፍ ስቴትን እና አክሽን ቫልዩ ሪሌት እናደርግ ብለን ምን አደረግን? this probabilistic function አለን policy of A prime given S prime 0 or 1 ነው የሚሆነው የኛው times action value over policy pi for S prime and A prime ይሆናል። ስለዚህ ይሄንን ወደዚህ ስናመጣ value of state over pi for all states ማለት ነው is simply the sum of the action values over pi for those actions used on that state S ማለት ነው። ይሄ ማለት በቤልማን ኢኩዌሽን ፎርም በዚህ መልኩ ሪፕሬዘንት ሊደረግ ይችላል ማለት ነው። So now let's talk about Bellman expectation equations. So basically Bellman expectation equation is an equation that lets you explore the environment. A prediction equation ነው ማለት ነው። So last time ምን ብለናል? We have prediction, we have control ብለናል በሪንፎርስመንት ለርኒንግ ፕሮግራም። So Bellman expectation equation የምንላቸው action value over pi እና value of state over pi are there to let you calculate or explore the environment, to know what will the environment provide, what will be the consequence of action A on some environment, general environment, which is characterized by a set of possible states and a set of possible actions S and A respectively. So from value of state over pi ለምሳሌ ስታዩ እዚህ ጋር ምን ይሆናል? እቺ እዚህ ጋር አለችን summation of simply it's a cumulative reward, discounted cumulative reward ነው እንደምታዩት። immediate reward አለ፣ discounted reward አለ, but it's what stochastic ነው። it's stochastic ነው። እዚህ ጋር ስትመጡ ደግሞ it has flag. basically ምንድነው for all actions ስለሆነ ፖሊሲ multiple actions ሊሰጠን ስለሚችል for all actions አክሽኑን ልትጠቀሙት የምትችሉበት ቦታ ከሆነ this will be 1 otherwise 0. so flag ለማድረግ የሚጠቅመን ነው ኢኩዌሽን ማለት ነው። the same is true for this one. Here the difference is action value ስትሄዱ here the flag is here inside the action value calculator. ሁለተኛው ኢነር ሉፕ ላይ ነው የሚኖረው። The second important equation is the Bellman optimality equation ነው። Bellman optimality equation ደግሞ ምንድነው? ሁለተኛው የሪንፎርስመንት ለርኒንግ ፕሮብሌም ነው የሚያሳየን which is control ያለው ማለት ነው። እዚህ ጋር ያለው again MDP ዲፋይን የሚደረገው as a tuple of states, actions, prediction, reward and discount ነው። ዲፍረንሱ ግን ምንድነው? Here we compute you see the maximum discounted cumulative reward for both of these ማለት ነው። so maximum compute እናደርጋለን። so in case of value of state over value of state, optimal value of state, the maximum of value of states over pi compute ይደረጋሉ for all pi's ማለት ነው፣ for all policies። እዚህ ጋር ስንመጣ immediate reward plus discounted ምንድን ይሆናል ማለት ነው? discounted sum of the probability of some state given action and S and the maximum of action values ማለት ነው። action values over pi compute ይደረጋል ማለት ነው። so we call this Bellman optimality equation እንለዋለን ማለት ነው። so value of state over pi እንግዲህ ምንድን ነው? the higher value achieve ሊያደርግ የሚችል ፖሊሲ ያሳየናል ማለት ነው። so there can be no policy with a higher value than a policy which yields the value of state, the optimal value of state እንደማለት ነው። okay so yeah, I think I will let you read this one. It's not a new concept. For instance, just the value of the optimal value of state ያለበት environment ወስዳችሁ ግሪዲ አልጎሪዝምን ባለፈው የተማርነው ግሪዲ አልጎሪዝም አፕላይ ብታደርጉ then that algorithm is rest assured ምንድነው ኦፕቲማል ይሆናል ማለት ነው። so እሱን ኮንሰፕት በተወሰነ መልኩ ነው የሚያሳየን። ቤልማን ኢኩዌሽን በተወሰነ መልኩ ያሳየናል ማለት ነው። So let's see how to solve reinforcement learning problems using Bellman equation. እንግዲህ ቅድም ምን ብለናል? አንደኛው ቤልማን ኤክስፔክቴሽን ኢኩዌሽን ቤዚካሊ ፕሪዲክሽን ወይም ፖሊሲ ኢቫሉዌሽን ልንለው የምንችለው ነው። ሁለተኛው ፕሮብሌም ደግሞ ኦፕቲማይዜሽንን ያሳየን ቤልማን ኦፕቲማይዜሽን ኢኩዌሽን ያለው እዚህ ጋር ቤልማን ኦፕቲማይዜቲ ኢኩዌሽን ያለው አለ ማለት ነው። ስለዚህ ሁለቱ የሪንፎርስመንት ለርኒንግ ፕሮብሌሞች እነዚህ ናቸው። መጀመሪያ ፖሊሲ ኢቫሉዌሽን እንሰራለን which is value of state over pi action value over pi ይሰራል ቅድም እንዳያችሁት። ሁለተኛው ኦፕሬሽን ደግሞ ምን ይሆናል? once list of value of state over pi and action values over pi ካለን then which one is better የሚለው optimal Bellman optimality equation በመጠቀም the maximum of action values the maximum of cumulative discounted cumulative rewards compute እናደርጋለን for optimal action values and optimal value of state respectively ማለት ነው። Okay, let's consider this simple MDP. Let's say we have three states S1 አብራችሁ ናችሁ?
Yes.
Okay. Let's consider these three states S1, S0 and S2 consider action አለን. Look, let's say our initial state is S1 ነው እንበል. So the list of possible actions from S1 ማን ናቸው? ለምሳሌ ከS1 list of possible actions A1 እና A2 ናቸው። ስለዚህ for all actions ስንል ከዚህ ስቴት ሊወሰዱ የሚችሉ አክሽኖችን ነው usually consider የምናደርገው ማለት ነው። Okay? ያቺ ፓይ ፕሮባቢሊስቲክ የሆነችው ፓይ ፍላግ ያልኳችሁ ኢኩዌሽን ቤዚካሊ ከዚህ የሚነሱ አክሽኖችን ወይም ከዚህ የሚወጡ አክሽኖችን ከማይወጡ አክሽኖች ለመለየት የምትጠቅመን 0 እና 1 ማድረጊያ ፍላግ ናት ማለት ነው። So here we have three states, two actions. From S0 you can use A2, from S0 you can use A1 አይደለም? From S2 you can use A1, from S2 you can use A2. በሁለቱም ኬዝ ወዴት ነው የሚወስደን? To the same S0 ነው። So let's define the invariants. Let's say ቅድም እንዳልኳችሁ the actions have a 0.9 probability አላቸው ብለን እናስብ። Okay? Probability of action ማለት ምንድን ነው? Given this state, the probability of this A1 ምንድን ነው እያለን ነው? 0.1. Look, ምን ያህል unrealistic እንደሆነ ማለት የምናወራው ነገር in a good way unrealistic ነው። ለምንድን ነው? If we try to make it realistic, it's not going to be that suitable for the academic environment. ለምን? Probability of A1 from here is different from probability of A1 from here ለምሳሌ አይደለም? Different ነው usually. ግን for the sake of understanding this easily, we are saying the actions have a 0.9 uniform probability of success እያለን ነው። ሁለተኛው ደግሞ they have 0.9 probability to remain in the same state እያለን ነው። So ምን እያለን ነው ማለት ነው? አንድ አክሽን አፕላይ ተደርጎ ኤጀንቱ ፊት የነበረበት ስቴት ላይ የመውሰዱ ፕሮባቢሊቲ 0.1 ነው። ትራንዚሽን የማድረግ ፕሮባቢሊቲ ደግሞ 0.9 ነው። ኢኒሻል ስቴት እንበለው ይሄ S0 ላይ ኢንድ አፕ የሚያደርጉ አክሽኖች በሙሉ ሪዋርዳቸው 0 ይሁን ይላል። ኤንድ ከዛ ውጭ ደግሞ የሆኑትን -1 ይሁኑ እያለ ነው። ኦኬ then we have RT0 for all transactions that end up in S0, RT-1 for all transactions. ለምሳሌ A2 እንየው ለምሳሌ ከS1 ወደ S0 ይወስዳል። ስለዚህ A2ን አክሽን ቫልዩን ከዚህ አንጻር ስናስበው ሪዋርዱ ስንት ይሆናል ማለት ነው? -1 ይሁን እያለ ነው። ኦኬ -1 ይሁን እያለ ነው። ለምሳሌ S0 ላይ ሄደን A2ን ብናየው A2 again ምን ይኖረዋል? -1 ሪዋርድ ይኖራል። ለምን? A2 takes you to S1. So this is what it is saying ለማለት ነው። So let's evaluate this problem now. Let's consider a discount factor gamma 0.9 consider አድርግ እያለ ነው። ምን ማለት ነው? ኢሚዲየት ሪዋርድን ካገኘህ በኋላ ቀጥሎ ያሉትን ሪዋርዶች የቀጥሎ ያለው ስቴት ላይ ሆነ ኮምፒውት ስታደርግ for specific action ምን አድርግ? በ0.1 ሪዋርዱን ዲስካውንት አድርግ እያለ ነው። So let me start from this one and take action A1 ለምሳሌ A1ን action value compute ማድረግ ብፈልግ then the action value of A1 at S1 ነው compute ማድረገው it is what? -1, right? It is -1. Then we have the probability for successful transitions which is 0.9. ስለዚህ 0.9 times what ይሆናል? 0.9 times -1 ይሆናል። S0 ላይ ነው ያለ ነው። Next state is S0. The probability of A1 ጊቨን ኤስ 0 ያው ኮምፒውት የምናደርግበት ኤ1 ስላለ ዋን ዋን እያደረግ ነው። ፓይ ኦፍ ኤ ጊቨን ኤስን ዋን ዋን እያደረግኩ ነው እየሄድኩ ያለው ለሲምፕሊሲቲ። ኤስ 0 ኤ1 ምን ይሆናል? አጌን ትራንዚሽን ስለሚያስደርገን ምን ይሆናል? ማይነስ ዋን ይሆናል። ፕሮባቢሊቲው አጌን 0.9 አለ 0.9 ታይምስ ትራንዚሽን ስላደረገ ማይነስ ዋን የምናገኘው ሪዋርድ አለ። በት ዲስ ሪዋርድ ስፔሲፊካሊ ሹድ ቢ ዲስካውንትድ። ለምን? ዲስካውንት ፋክተር ፎር ኔክስት ፎር ነን ኢሚዲየት ሪዋርድ ስንት ነው ብለናል? 0.9 ብለናል። ስለዚህ 0.9 ጋር ይሄዳል ማለት ነው። ከዛስ ኤዋን ይመጣል ተመልሶ እዚህ ይሄዳል። is there any a1 after this? yes kind of cyclic ይሆናል። ሶ እዚህ አካባቢ ይሄዳል፣ ወደዚህ ይመጣል፣ ይሄዳል፣ ወደዚህ ይመጣል። sometimes ዲስካውንት ፋክተሩ እየበዛበት ስለሚሄድ ምን ይሆናል? ኮንቨርጅ ያደርጋል፣ ስታፕ ያደርጋል ማለት ነው። even though infinite ቢመስልም okay. So I tried to compute such similar type of solution like using paper. Okay, I'm sorry for this one. I couldn't write using my mouse. ስለዚህ በዚህ መልኩ ወረቀት ላይ የሆነ ነገር ጀምሬላችኋለሁ። refer the book, refer any related እንትና simply አሁን በሄድነው መሰረት for every of for probability ለብቻ ከፈለጋችሁ ትችላላችሁ because the probability እንዴት እንደሆነ እዚህ ጋር already ያስቀምጠናል። ለምሳሌ probability of a1 given s1 ለምሳሌ or the probability of some reward minus 1 given action a1 and state s1 ስንት እንደሆነ አይተናል። some kind of minus 1 እንደሆነ አይተናል። ስለዚህ minus 1 sorry with some kind of probability ቅድም የሰራነው 0.9 እንደሆነ አይተናል። ለምን? ትራንዚሽን ስለሚያስደርገው እያለ እዚህ ጋር probabilityውን ለብቻ እንሰራለን በዚህ በኩል እንደምታዩት ኦኬ። ልክ በዚህ መልኩ እንደምታዩት then ይሄን probability ፍላጎቹ አሉ for a read this slide and you will understand what I have been talking about throughout this class ማለት ነው። so እንግዲህ ምን እያልን ነው የነበረው? reinforcement learning problem ሁለት አይነት አስፔክቶች አሉት እያልን ነበር። አንደኛው አስፔክት የፕሮብሌሙ አስፔክት ማለት ነው ኤክስፔክቴሽን ኢኩዌሽኖች የሚሰሩት ነው which is exploration ነው prediction ነው what is the value of state over pi ነው basically. The second one is Bellman optimality equation address የሚያደርገው ደግሞ ምንድነው? which one is better ነው። for that in model based environment we do have techniques, iterative techniques. We have been talking about them, about those techniques because we have been talking about Bellman equation for instance here, right? So the techniques are already discussed but here we will give them names. The name for those techniques we have been discussing about is dynamic programming, and dynamic programming is a technique that lets you compute the value of state over pi, the value of the action value over pi, and choose the best value of states, value of state over pi, or choose the best policy or the best value of state ማለት ነው። So basically we use models, assumption እሱ ነው ቅድም ስንጀምር ብለናል። we use models and we apply dynamic programming. When we say dynamic programming we are saying value iteration or policy iteration. Okay, value iteration ወይም policy iteration ቴክኒኮችን እንጠቀማለን ማለት ነው። So the next section of this chapter is all about dynamic programming or specifically value iteration እና policy iteration የምናይበት ነው። ነገር ግን a way to come up with Bellman optimality equation is also non-model based technique basically. So it's called sample based technique or model free technique ይባላል። For this we will see in the next chapter, actually this is a separate chapter, we will see how we can apply Monte Carlo algorithm, different types of varieties of Monte Carlo algorithm. We will see temporal difference algorithms, sample based algorithms, okay? And also in the next subsequent chapters we'll talk about Q-learning, which is mainly based on action value. SARSA, we have been talking about SARSA because we said Markov decision process is a sequence of states, actions, rewards, right? States, actions, rewards. So this is state, action, reward, state, action, like that. So this is the algorithm, basically. We'll talk about this one in separate chapter, this one in separate chapter, and this and temporal difference in separate chapter. But as part of this chapter, value iteration and policy iteration will be discussed. I might send you pre-recorded video given the time constraint, okay? I might record a video after having tea or something, and I will send it to you now. This Saturday, we should have additional class, okay? It's must, actually, we shouldn't compromise it. Someone, I think it's Dr. Bakal, he sent me, we are left with 1 month to finish this class. So I guess we should have more compensation classes. Okay, actually ምንድነው chapter 4 and 5 are very relevant portions of the first part of this course, classic reinforcement learning. እሱን ከሸፈንን ሌላኛው ያን ያህል ኢሹ አይደለም። ምን ለማለት ነው? ዲፕ ሪንፎርስመንት ለርኒንግ ላይ ነው የምንገባው ማለት ነው። ስለዚህ ዲፕ ሪንፎርስመንት ለርኒንግ በፕሮጀክትም አንድ ሁለት ሌክቸር ከሸፈነ በፕሮጀክትም አድሬስ የምናደርገው ይሆናል ማለት ነው። እና መብራቱ you have question?
ጥያቄዎች አሉ ዶክተር።
እሺ ፕሊዝ ፎርዋርድ them።
እሺ እዚህ ቤርማን ኢኩዌሽን ላይ የኢንቫይሮንመንቱን ኤክስፕሎር ለማድረግ ያየናቸው ነገሮች አሉ እና አክሽኖቹ ራንደም አድርገን መውሰድ እንችላለን። ሳይሆን ጊዜ ለፔዳጎጂ ብለን የወሰድናቸው ነገር ግልጽ ስላለ
ኦኬ ሶ ለምሳሌ value of state over pi ምንል ከሆነ basically actions are not random but they are determined by this function called pi ማለት ነው። አክሽኖቹ ፓይ በሚባለው ፋንክሽን ነው ዲተርማይን የሚደረጉት። በሪያሊቲ እሱ ነው። ምን ማለት ነው? አንድ አሲው የሆነ ፋንክሽን ፓራሜትር ታይምን ይወስድና ለዛ ለወሰደው ታይም ፓራሜትር እና ለከረንት ስቴት ኦፍ ዘ ኢንቫይሮንመንት እንደ ፓራሜትር ወስዶ ከነሱ ከስቴቱ ጋርና ከጊዜው ጋር አብሮ የሚሄድ አክሽን ጀነሬት የሚያደርግ ፋንክሽን አድርገህ አስበው። that is policy right? ስለዚህ በሪያሊቲው ስንሄድ in model based environment ላይ the approach ምንድነው የሚሆነው? actions like generated by the policy pertinent to that specific moment ነው ኮንሲደር እየተደረጉ የሚሄዱት። ነገር ግን ያንን ahead of time ስለማናውቅ ምን እናደርጋለን? we exhaustively list actions and for each of that action ማለት ነው for each of those possible actions action ቫልዩዎቹን ወይም ቫልዩ ስቴቶችን ኮምፒውት እያደረግን ሰም አፕ እያደረግን እንሄድና the best result የትኛው ነው የሚለውን እናያለን ማለት ነው። ሶ ሁለት አይነት አፕሮቾች አሉ። አንደኛው አፕሮች assuming actions are randomly picked ብለን አስበን መሄድ እንችላለን። ግን this is not ለኢዝ ኦፍ ፔዳጎጂ ሊሆን ይችላል። the reality is not that አይደለ? ፖሊሲ የሚለው ነገር ራሱ ሀሳቡ ምንድነው? at some point የሚወሰደውን አክሽን at some other point ከሚወሰደው አክሽን አንፃር መለየት ነው። አላማው ደግሞ ምንድነው? እነዛን በመለያየት ውስጥ የሚገኝ ኦፕቲማሊቲን አቺቭ ለማድረግ ነው ማለት ነው። ስለዚህ በራንደም አንመርጥም። አጭሩ መልስ መብራቱ መቀጠል ትችላለህ።